Bismillahirrahmanirrahim. Assalamu alaikum. This is last topic of membrane separation, pervaporation. Before this, we have discussed two major application of membrane, and those were reverse osmosis and gas permeation. Reverse osmosis is majorly applied for cleaning of water, and its major application is for cleaning of seawater, that is called desalination. Also, we discussed that this membrane reverse osmosis phenomenon can be applied for cleaning of different industrial water as well as domestic, all other waters which are contaminated due to human activities. But major application of reverse osmosis is for desalination, and desalination is the cleaning of or removal of salts from seawater to make it like drinkable. And then after that, in the last lecture we have discussed about membrane application for gas permeation, in which we studied that membranes can be applied for separation of various gases, and in that application we discussed that porous and non-porous both membranes can be used, but it's better to use non-porous membrane or dense membrane because mostly gases have small diameter and it will be difficult to separate them with the help of like size exclusion phenomena. As compared to that, the better is to use dense membrane, and because diffusion or permeability of various gases through various polymeric membranes is different, and based on this phenomena of diffusion difference or permeability difference, you can easily separate various gases. Then this last topic of pervaporation, today we have to talk about this in detail, and this will include the introduction, then mechanism, how pervaporation takes place, and then finally applications, membrane plus modules used in this membrane phenomena. Let's start with the need for this main pervaporation, why we go for pervaporation. Actually, there are two important categories of separating various main hydrocarbons or various components, and those separations are difficult. What are those separation? These are two separation, like if you are separating azeotropic liquids or the mixture where azeotrope is formed, you know that it is very difficult to separate them. When azeotrope is formed, you can't go for distillation, then you look for other techniques, and maybe you can go for like liquid extraction or absorption. But when we started the membrane, we said that membrane are better as compared to those other separation technologies due to various advantage which we discussed at the start of membrane when we started with the membrane, that why these are better as compared to other techniques. Although you can separate these azeotrope with the help of maybe liquid extraction or maybe absorption, but membrane separation will be better for such kind of separation. The other are when there are very small differences in the boiling characteristics. Again, you know that it is difficult to separate them with the help of distillation, because when their boiling points are closed and their volatility differences are very small, so it's not possible to separate them. Although you can separate them, but you will need very large size equipments, and energy consumption is way higher as compared to simple separation. So in these cases, pervaporation phenomena can be used, or pervaporation membranes are used for this separation. And by the way, this mixture, both this is the liquid mixture, and again which have small difference in boiling. What does this mean? It means they will also exist in the liquid form. So overall you can say that this pervaporation technique is used for separation of the liquids. As compared to this, like gas separation, that's also can be used for like these hydrocarbon or other gases separation, but they exist in the form of gases. Like RO was for water, then gas separation can be used for any mixture of gases, and this pervaporation is used mostly for the separation of the liquids, and most of the time its application we will discuss later on in this lecture, that it's for hydrocarbon separation, and when they exist actually in the form of liquid mixture. So pervaporation is the best way to separate them. So its name like this pervaporation, this is combination of two words, uh, pump selective and then there is evaporation. So if you just take from here per and then just vaporation, so pervaporation is the combination of this. What does this mean? Pump selective membrane mean you know that this is type of membrane in which we have a asymmetric membrane, and that consists of more than one layers. Like there can be dense as well as porous membrane structure. It is a combined structured membrane, or you can say it's composite type membrane. And then there is evaporation. I mean you are just evaporating anything which is in the form of liquid to the vapor. So in this technology, when you will be using the membrane, actually with the help of this pump selective membrane, you are making the separation. At the same time you will be changing the phase of those components which are being separated. So this technique will involve actually this differs from other like techniques which we discussed here, reverse osmosis and gas permeation, as well there is dialysis which was not included here in our main subject. But those all type of membrane when you will use for these application like dialysis, reverse osmosis or gas permeation, there were no phase change involved. At least you remember from reverse osmosis and gas separation or gas permeation which we have discussed, that when you were using these membranes, at least there were no phase change. In the case of water, you remember that when water passed through this membrane, that remains in the form of liquid. As well, when gases were passing through the membrane, they were supposed to stay in the form of gas, and they stay in the form of gas. They didn't get condensed. But in this technique, pervaporation, there will be phase change. How phase change will take place, we will look at this later, but at this moment at least its feed is in the form of liquid, but on permeate side it is converted to the vapor. I mean all those components which pass through the membrane are permeated, and as collected as permeate they are in the form of vapor, while other its feed exists in the form of liquid, and retentate will also be living in the form of liquid. For example, here in this cell you can see that this is one cell on which this side there is a feed, and then membrane is installed inside this, and on the other end you are collecting like permeate, because here he is mentioned permeate as a vapor. So he mentioned here somehow vacuum is applied on this side, and when you are applying the vacuum, some component which can pass through the membrane like these white color dots, this component can easily pass through the membrane, or they have good permeability, other have very low permeability as compared to this. So when they get separated, they reach to the other side of the membrane, they are evaporated, they are converted to the vapors. And later I will talk why we go for our just let's discuss it here. Few lectures back, if you remember, we discussed the comparison between I think that was some starting lecture of membrane separation. So we discussed there like if you are using the membrane and various diffusion of various species, actually we were comparing those, like there is diffusion of solid, diffusion of liquids and diffusion of gases through the membrane. So if you recall, diffusion of gases was the highest, or if something when is existing in the form of vapors or gas, that can easily diffuse through the membrane, or their diffusion was fast. There was comparison between I think molecules of water which were passing in the form of either solid, liquid or vapor through various membrane components. So their diffusion was different, and the highest diffusion was possible when they were existing in the form of gas. So here when some species just pass through this membrane, and if it is converted in the form of vapors inside the membrane, so its diffusion will increase, and when its diffusion is increasing, definitely its separation is higher as compared to other component, which will diffuse like slowly. Overall, with this you are increasing the rate of diffusion, rate of separation when you are using pump selective membrane. Hopefully it's clear to you. So again we will discuss this point later on in the lecture, but the major purpose here pervaporation is to evaporate the species which are diffusing through the membrane, and when we are just evaporating, with the help of this, actually you are increasing the rate of their diffusion and separation through the membrane. Here you can see another system in which you have a mixture of various petrochemical and water molecule, and there is a membrane here, and this membrane is hydrophilic membrane. So hydrophilic, which is which attracts the water, hydrophilic, which has affinity for the water, and there is other term that's called hydrophobic. So they they repel the water, they are not water loving. This hydrophilic will attract the water, and when they have good separation capability for the water, or water can easily diffuse through this membrane. So when you are using this membrane, on the other side, when water reaches water, vapors are formed. And by the way, this how this evaporation take place, because something is in the form of liquid is on the one side of membrane, and when it passes through the membrane, how it gets converted to the vapor. We apply actually the vacuum on the other side, and when you are applying the vacuum, actually you are decreasing the pressure on the other side of membrane, and because in order to convert something from vapor to the liquid to the vapor, you just go either for heating, you increase its temperature, and when its vapor pressure reaches or becomes equal to the surrounding pressure or ambient pressure, then its vapors are formed. Now here when we are decreasing the pressure, we are creating the vacuum. Due to this, when you are decreasing the pressure, you are decreasing the surrounding or ambient pressure, and when ambient pressure is reduced, their boiling point is reduced, and they can easily boil even at low temperature. Due to this, they are converted to the vapor. For example, here if we are considering the water, if it was ambient temperature, ambient pressure on this side, so for this you will need temperature of 100 degrees C, but when you reduce it, definitely it can boil easily even at temperature which is below 100. This membrane here, there are two phenomena shows to you, like there are hydrophobic and hydrophilic membrane. When you are going for these separation by using pervaporation, later on you will look at the application that a lot of application of this pervaporation membrane is for removal of water through removal of water from various hydrocarbons. So if you use such membrane which is water loving or hydrophilic, so in that case water will easily diffuse through that membrane and can get separated. While on the other hand, if you are using the membrane which repel the water, so in that case that membrane should have affinity for other component instead of water. For example, water is in large amount and some other hydrocarbon are in very small amount, so we will prefer to just pass those hydrocarbon through the membrane and can get them separated. But if hydrocarbon are in large amount as compared to water, so in that case we will prefer to remove water through this membrane. So in that case those membrane will be used at like hydrophobic if you want to repel the water away from the membrane, but if you want to pass water through the membrane, so then you will prefer the membrane which has affinity for the water. So in these both cases, actually feed enter, pass through the membrane, and on the other side they are converted to the vapor. Again same like phenomena here, you will be applying vacuum. Membrane, this PV stands for this pervaporation membrane, and these pervaporation membrane are used for actually pervaporation membrane application. These currently commercial application of pervaporation membrane include actually dehydration of ethanol. if you have to remove the water from ethanol when ethanol is produced, and this it also contains water. So in order to remove water from ethanol, these pervaporation membrane are the best available technique. Then there is dehydration of other organic alcohol. This is ethanol, mean if suppose you have propanol, methanol, ketones, esters, so also water can be removed from those hydrocarbons. And then there is removal of dissolved organics from water. In this application, water is in large amount. If other some small amount of hydrocarbons is there, organics are there along with water, so those can be removed with the help of this pervaporation membrane. If you remember, when we discussed liquid extraction, in that there was at the start of that lecture there was some application of this liquid extraction for removal of water from acetic acid. So in such case, like you can either use that liquid extraction or membrane, but as you have studied now that membrane are better as compared to all those techniques because they are compact, they cost less as compared to other technique, the equipment are smaller in size, they are easy to install, and various other advantage membrane can be preferred as compared to other techniques. The separation of close boiling mixture, you know that it's again difficult to separate them. The major point at the start we also discussed that close boiling organic chemical are difficult to separate. So for those application, these pervaporation membrane are good. And because this now benzene and cyclohexane, they will be close to each other, their size will also be close, diameter of the molecule as well, their boiling points are close to each other. So in this case, you can't go for distillation, then it's better to look for other technique, and among other this membrane separation is good. So you can separate this mixture of benzene and cyclohexane by using these membranes. So their application to separation of other hydrocarbons, some difficult separation, maybe if they are existing, there are a huge mixture and they are at elevated temperature, mean they are available at high temperature. So their separation, when temperature is high, then polymeric membranes are not that good. You have to use some other membranes which can separate them, and those are inorganic membrane, and those advanced membrane inorganic membranes can be used, or maybe organic inorganic composite membranes which can exist or which can perform separation at high temperature, they can be used for such kind of separation. But at the end, just to conclude this application, membranes, pervaporation membrane have found a lot of applications on industrial scale for various separation of majorly closely boiling hydrocarbon, as well as to remove water from various hydrocarbons mixtures. Let's look at the mechanism, how does it take place. So somehow we have discussed few points before this, but overall that feed mixture here is liquid, feed entering to this system is liquid. Then some components in this feed, in this mixture, can permeate through the membrane and they are evaporated. On the other side of the membrane, when they reach to the other side of membrane, they get evaporated. Actually they evaporate as a result of partial pressure on the permeate side being lower. Suppose if mixture is just passing through this, then you will look at the partial pressure. If out of mixture only one component is passing, then we will say its boiling temperature or its saturation temperature. But if 2 or 3 component can diffuse through the membrane, so definitely then you will be looking at partial pressure of each component. So they are at the end actually lower than the saturation, their surrounding temperature is lower than the saturation pressure. Surrounding pressure when will be lower, then due to this vacuum, due to this low pressure, evaporation take place and their phase is converted from liquid to the vapor. The driving force is controlled by applying the vacuum. Here driving force, we discussed this, that driving force for reverse osmosis was the pressure, high pressure on the feed side, and low pressure on the permeate side as well. For gas separation, very high pressure was being used on the feed side, and low like almost ambient temperature was used on the permeate side. But in these membrane, you mostly bring the liquid at not very high pressure, sufficiently high pressure, like not like the pressure which we discussed earlier, like in gas separation membrane. If you remember, it can vary from somehow 10 atmospheric to 150 atmospheric on feed side. So here you bring those usually at low pressure, but on the permeate side actually you are providing the vacuum. So now when you are providing the vacuum, definitely you are creating the pressure difference here. So with the help of that, this separation take place. So let's look at this membrane. It is again asymmetric membrane. Most of the time we are using asymmetric membrane for all application which we have studied: reverse osmosis, gas permeation, and again this is again asymmetric membrane. And the phenomena is the same, or the reason is the same to use asymmetric membrane, because you have to apply the pressure difference on the both sides of membrane, and it is not possible for the dense membrane simply one sheet to support that high pressure, otherwise its rupture will take place. And in order to avoid that rupturing, you are using asymmetric membrane. So they are like combination of porous and non-porous membrane. At the top there will be non-porous layer or dense layer, which is mainly for separation, and then there are porous layers. Sometimes one layer, sometimes two layers are possible. Then it is asymmetric membrane, and they are used for supporting the membrane. On the one side, feed side, you have a liquid feed, and it's available at pressure P1, and that consists of two species, A and B. Just look here, like feed to the membrane module is a liquid mixture which is at pressure P1. That's high enough to maintain a liquid phase. Yes, here pressure should be high enough that you can maintain a liquid phase. It didn't get vaporized on this side of membrane. Feed side, evaporation should not take place. Pressure should be sufficiently high that all the components which are available as the feed, they stay as a liquid when this exists on the feed side. And even when some components are removed through this, like A and B component, when feed enters from this part and it is going through this membrane, and on the other end it leaves, but when it is passing along the membrane, some component definitely will diffuse through the membrane, which are like A, and some part of the B. As you have seen here, he has mentioned that fast pervaporation, it means fast permeation. So component A, if you are considering A and B, just two components, so component A has fast permeation, it's mean majorly A will get diffused through the membrane and its separation take place from B. While as already you know that membranes are not like 100% selective for one component, some part of the B will also diffuse through this membrane, but its permeation is very slow. As in the first diagram we have seen, there were some red and white circles, and white circle parts can diffuse in the large amount as compared to other which were in the form of red. So this also will pass through, but small amount will pass through. So even when this some components are feed is actually depleted, means some component has been removed from this feed, they have permeated through the membrane, so still it exists in the form of liquid when it is leaving this feed side as a retentate. On the other side of membrane, you have pressure P2, and which is most of the time vacuum. You apply here the vacuum, and I already told you that the purpose of vacuum is to reduce the ambient pressure, and when you are reducing ambient pressure, you are converting the phase from liquid to vapor. Here in this is the membrane module. In this he has just separated this in the two parts. So let's talk about this somehow 1 or 2 minutes later. A composite membrane are used here, and the reason of using composite membrane I already told you, that to support high pressure. So this composite membrane is used, which is selective for the species A, but for somehow finite permeability for species B. Small amount of B can also pass through this composite membrane, and reason is to use this membrane to be to operate this process at high pressure or pressure difference. The dense thin film side of membrane is in contact with the liquid side. Yes, this is important when you are placing these membranes. So as this membrane is a combination of porous and non-porous membrane, so dense membrane film side, which is major separation layer or active layer, that should be placed on the liquid side, because through your liquid something has to diffuse and then pass to the other side of the membrane. So this active layer should be on that side from where you want to make separation. On the other side only those components exist which are actually separated, but on feed side there will be a mixture, so this dense thin film side should be on that side. And this is same for even RO and gas separation. When you are using, you use this thin film like dense membrane, which is active layer. This is usually on feed side. At the end of the day, when permeate will be like contain more amount of A, and retentate will contain more amount of B or B species in large amount. The vapor phase may exist here on the permeate side, and that's usually enriched in A. This vaporization may occur even during the passage through the membrane. There the downstream phase, downstream this is upstream from where this diffusion is starting. On the other side, this is downstream side from where these species A molecule will be leaving the membrane. This is downstream, and other upstream from where it is entering. So through this membrane, when this A, which is in the form of liquid, this diffuse through the membrane. While passing through the membrane, even inside membrane there are two zones, liquid phase zone and the vapor phase zone. What does this mean? That through this membrane, when it will pass, it will exist in the form of liquid up to some extent, up to some point, but later it will just get converted to the vapor phase. And why it's converted to the vapor phase? As we are using here the combination of porous and non-porous membrane, when it will be passing through the dense or non-porous part, it will be existing in the form of the liquid. But as it moves or as it is passed through this dense towards porous part, or that part which contains pore, so in that part definitely there will be effect of this vacuum. So due to this vacuum, that gets converted from liquid to the vapor. So this vaporization has even taken place when this liquid or this component was inside membrane. It is not like when it reaches to the other side of the membrane it gets converted. Even inside the membrane, vaporization takes place. Right, here pervaporation, by the way, as we have seen that for vaporization you need the heat, or in order to convert the phase you have to provide some amount of the heat, and that's we are not usually heating here inside membrane. Actually we are just reducing the pressure and this phase change is taking place. But even when you are reducing this pressure, still some energy will be needed, some heat will be needed. That's called heat of vaporization. Even at its reduced temperature you still need some heat. So from where that heat comes? Actually this comes from sensible heat of the feed mixture. Out of that feed mixture, these molecules which are passing through the membrane or which are going through the membrane, they will just extract some energy of the other components which are available in the mixture. And due to this providing sensible heat of the feed mixture, you are providing actually the enthalpy of vaporization, or the heat needed for these molecule to get converted to vapor. So due to this phenomena, you prefer pervaporation in those cases in which this mixture is dilute in the main permeate or main component which is separated. So if that is present in the small amount, it will be more favored technique pervaporation. Why? Because then in that case you will need small amount of heat, and that can be easily provided through this mixture. Actually in this case you will not need to provide extra heat. You don't need to heat the feed to provide the later on heat of vaporization. But if your feed contains more or large amount of this permeate which you want to separate, so in that case, if feed is rich in the main permeate, it is present in the large amount, then number of membrane stages may be needed. More than one stage you will need. Why? Because in each stage small amount will be permeated, because energy needed for this heat of vaporization is coming from the feed, and you can provide somehow some amount of feed, but not for the all components which you want to separate. So you will just pass it to the other stage, but before passing it to the other stage, definitely we will need some heating. So reheating of the retentate between stages will be needed. Just look at this diagram here. You can see this is the one stage phenomena in which you are entering the feed through this membrane, and this is the membrane. In this membrane module, on the other side you have applied the vacuum. You can see this, this side vacuum is applied, and when you are applying the vacuum on this line, so this vacuum also affect this part, and due to this effect, more component can get separated. So retentate leaves, and this is just one phase. But if you are using more than one phases, so what will happen, your feed comes, you heat it up, and sometimes we heat it up because we provide the heat of vaporization later on needed while passing through the membrane to those components which you want to get vaporized. This pass through this membrane module in this retentate leaves, and there is a membrane. This is not some stream leaving, just indicated that this is membrane here. And on the other side here is permeate vapor. By the way, in this diagram it is shown that you are using the condenser, as well as here you are using the condenser, because when this is vaporized later, you just store it or you just pump it to somewhere by using just converting the phase, you are condensing it. And when you are condensing, in some parts are condensed, and while other, if still you know that condenser, if it is not full condenser, partial condenser you are using, so in that case some part of that feed which is entering to this is feed here permeate which is entering to this is converted to the condense, and some which stays in the form of vapor is just went through this line. Here in these cases we apply the vacuum with the help of vacuum pump mostly. Suppose there is another stage, so this retentate will go to the other stage, so it will just pass through another heater, so that you just heat it up, so easily this evaporation take place through this membrane. Next is about membrane material which you use for these pervaporation techniques. So membrane material and modules. Membrane material selection is critical in commercial application. Why it's critical? Due to some reason. Let's look at this. For example, for water permeation, hydrophilic membrane material are preferred. Why hydrophilic? Because if they attract the water in large amounts, so if some material you are using that's attractive for water, so more water will be attracted, and more easy or more better separation can take place for this mixture which contains water. For example, a 3-layer composite membrane is used for dehydration of ethanol, and water being the main permeate species. Suppose you are removing the water from ethanol, as we discussed that this is one of the largest application of these pervaporation membranes. So in that case you use 3-layer composite membrane. This is asymmetric membrane which consists of 3 layer, and those 3 layer, definitely one will be active layer and other will be just supporting layer. So let's look what are the material used here. Support layer is the porous polyester. Porous polyester here this is made up of polyester, but that's porous. When it is porous, definitely this will be the support layer, which is cast on the which is fixed on the microporous polyacrylonitrile or polysulfone membrane. This is the second layer, polyacrylonitrile or polysulfone, and again this is again microporous. So overall it seems here this will contain large pore as compared to this. Here this layer will contain small pores, and then there is the final layer which provides the separation, that is the active layer, and that is dense PVA, polyvinyl alcohol. So that's 0.1 micrometer, or sorry, maybe this is polyvinyl acetate, I think. PVA, just check for this kindly. PVA, polyvinyl acetate, I think it should be. So that's the active layer. Through this major separation take place. This will be like attractive, this layer will be attractive for the water, so water molecule will pass through this layer, and then they after passing through this dense layer, they pass through the porous sport layers, and through those porous layers, vacuum is already available, and this water which is passing in the form of liquid through this dense layer, it will get converted to the vapor. The composite combines here chemical and thermal stability for adequate permeability. This composite which you use, so that combines chemical and thermal stability here, as well as they provide the support. Chemical it should not react with like your layer which you are using on the top. It should not be reactive even with the hydrocarbon or chemical which you are separating. It should only be used for the separation, or it allow only water to pass through this. Hydrophobic membranes such as silicon rubber and Teflon are preferred for application when organics are the permeating species. In that case, then those this silicon rubber or Teflon, they don't attract water, they attract easily the hydrocarbon or other components. When this is not hydrophilic, it is hydrophobic, it will not attract the water, so water is not the major permeating species. In that case, other component like organics will be here major permeating species. This was all about the materials which are used. So in this case, you can see that actually here the material you have to select based on the separation which you want to take. Either you want to remove the water or the other organics from the membrane, or permeate species, which is your permeate species, then based on that you have to make this selection. Regarding modules, so mostly commercial membrane modules for this pervaporation. Sorry, this is VP PV, pervaporation. This is not like GP, this is not gas permeation, it is pervaporation. So for this pervaporation, mostly use plate and frame type modules, and there are the certain reasons for this module usage. So first reason is like you need here gasketing material, and those material which you are using for gasketing, they should be resistant to the organic solvent. As you know that here in pervaporation we are using the vacuum, and in order to like maintain that vacuum, definitely you will be needing gasketing, and gaskets, you know that these are just like structure which are used to avoid some leakage. So in order to avoid this leakage of pressure, to avoid this to maintain the vacuum, so you will be needing gasketing inside these equipments, these membrane separating equipments, and for that purpose plate and frame can be easily gasketed. From the start, when we looked at this various module, hollow fiber, spiral wound, like this plate and frame. So plate and frame, there are the plates, and inside that these membrane are in the form of frame, so you can easily gasket those, you can easily apply those gasketing materials, and due to this, these are preferred, like plate and frame. As compared to this, will be difficult to maintain that vacuum in the form of like spiral wound or hollow fiber. Just consider that when you will apply the vacuum, those fiber can't maybe maintain that vacuum as well. The other spiral wound module inside that vacuum is difficult to maintain as compared to this plate and frame. Then this material which you are using for gaskets, that should be resistant to the organic solvent, it is necessary. Then the other main advantage of this plate and frame is the ease of providing heat exchange for evaporation and high temperature operation. When you are using this plate and frame in these techniques, if you have to provide the heat inside this for this evaporation, one, we are reducing the temperature, although at the same time in some application maybe you need to provide the extra heat during this phenomena. So in plate and frame, easy to provide this heat. Their structure are such that inside those modules it is easy to provide the heat. Just for this purpose, go back to those modules and look at those. When you will look at the plate and frame modules, so they are structured somehow easily. There are the like plates and membranes are installed inside them, so there maybe you can dedicate some parts for heating purpose. As compared to this, again in spiral wound and in hollow fiber membrane, it is difficult to provide heating inside the membrane. Most of the time when you look at these PV, pervaporation, so your feed are generally clean because they are coming from the reactors. Mostly these hydrocarbon are produced in the reactors and they contain water, so you want to separate them, or even they are closely boiling hydrocarbon mixture, so these are usually the clean feed. These are not like the gases which can contain particle. These are not like the water which contains a lot of impurities. So here these are usually the clean. Due to this, most of the time you don't have any pre-treatment unit in such pervaporation membranes. Because you are operating them as well at the low pressure as compared to the other, I have told you already that they are operated at the low pressure as compared to the reverse osmosis and gas separation. So due to all these advantage, clean feed, operation at low pressure, so membrane fouling and damage is minimal in these type of membranes. So this membrane can get damaged due to high pressure as well, due to the fouling, due to accumulation of various other components on its surface. So that's very low in these kind of membrane which are used for pervaporation. Due to this, they can be used for up to 2 to 4 years. Most of the time, by the way, membranes you have to replace membrane like after 1 to 2 years. Sometimes you don't replace them, you go for the cleaning, and until unless they are not completely blocked or they are not providing sufficient permeation, so then you go for their replacing. But this is large time, 2 to 4 years. Let's look at some pervaporation membrane schemes which are used on industrial scale. So sometimes they are used separately, sometimes they are used in the combination of various other techniques. Like here there is one use for the hybrid process for integrating distillation along with pervaporation. It means there will be distillation as well as pervaporation. So to produce 99.5 weight% ethanol from a feed which contain actually 60 weight% ethanol. So your feed contain only 60% ethanol and you want to purify it to the 99.5 weight% ethanol. Actually it contains water, 40% water is in the feed, and you want to remove that water, and finally you want to get 99.5 weight% ethanol. So in this technique, the common technique which is used on industrial scale, that was distillation, and with the help of distillation you can see this first part of this PFD. So in this part, ethanol water feed enter to this distillation column, and then there is condenser and reboiler along with this. And at the end of this, when you look at the products, bottom product is purely water. At the bottom from this reboiler you are getting the water, so that's pure water. Okay, you have separated some water, and from the top definitely you will be looking for the lighter component ethanol to be obtained as your product. Then you are looking for the product of purity 99.5 weight%, but here its purity is 95 weight% from this. And even if you install these equipment of distillation, maximum what you can reach is 99.5 weight% ethanol water. Above this, actually azeotrope is formed and you can't separate further. If you want to go for further separation with the help of distillation, maximum possible is this 95.6 weight% ethanol purity. Still there will be some amount of water present with this, like almost 4.4% water is there. So in order to avoid this water, to remove this water, to make it purified up to 99.5 weight%, this part is sent to this which is mixture of water and ethanol, that is sent to some membrane, that's pervaporation membrane. And this membrane is hydrophilic, which allows water to pass through this membrane, and then retentate will be the ethanol. So when it passes through this membrane, the distillate is sent to the pervaporation unit, and your permeate is 25 weight% alcohol. Permeate, majorly water will pass, and still through this membrane some alcohol is lost, and that's overall composition is there 25 weight% alcohol, and 75% will be definitely water, while the retentate side is 99.5% pure ethanol, which was your requirement. So with the help of this membrane you can achieve this separation. Now looking at this permeate, because this contain this is not only water, this contains sufficiently large amount of this ethanol, 25 weight% ethanol. So what you will do, this will be in the form of air vapor. So you just condense these vapors, and with the help of this condensation, then you bring it to some phase separator. In that phase separator, actually this liquid and vapor, all that, this is not definitely complete condensation, somehow some part of this is condensed and some is not condensed. So here phase separation takes place. The component which is in the form of vapor, they are just separated from here, and other which is in the form of liquid, they are pumped back to this main distillation unit, because we don't want to waste this sufficiently large amount of alcohol. So inside this here you are applying the vacuum. So this vacuum is actually applied for this pervaporation through this line, through this equipment. Here when there is a vacuum, so here separation through vacuum will take place in this pervaporation. So in this example, actually the purpose here is to separate this water and ethanol, and which can't be separated with the help of this distillation. At the end you have to go for this integration with PV membranes. Here the membrane uses cellulose acetate based composite membrane with the active layer of polyvinyl alcohol. This is two layer membrane, cellulose acetate and polyvinyl alcohol, and active layer is polyvinyl, and that is attractive for water, which allows in large amount water to pass through. That will be hydrophilic membrane. Other its usage is here, for example, for removal of VOCs. VOCs are volatile organic chemicals, for example toluene and trichloroethylene, benzene, xylene. A lot of these are considered under the category of this volatile organic chemical, because they are usually volatile at even low temperature like room temperatures. From wastewater, pervaporation with hollow fiber module of silicon rubber. So here you are using silicon rubber, and if you remember from few slides back, I told you that when you want to pass these organic chemical to pass through the membrane, you use such membrane like rubber or Teflon membrane. So this will be a hydrophobic membrane. So in this membrane, when you bring this wastewater, you are just bringing it to this membrane module, and inside this membrane module you are using the membrane which allows organic chemicals actually to pass through, and they can get separated. Why we are using this, by the way? Because here the water is in large quantity, we don't want water to pass through this membrane. Definitely we will want all those components which are in small amount to pass through this membrane. So in through this silicon rubber membrane, those organic chemical, volatile organic chemical pass through this membrane, and they just diffuse, or they just get permeated to the other side of the membrane. And this separation takes place when they are just permeated in the form of vapor. You condense them, because this membrane again will not be like 100% only organic chemical permeate. Some amount of water is also permeated, so you condense them, and after condensation you pass it to the three-phase separator. Three-phase separator are actually those separator in which there is one vapor phase and other are two liquid phases, and among those two liquid phases, one is totally volatile organic chemical rich, most of those will be volatile, while other there will be water rich liquid. So here there will be water as well as some amount of these volatile organic chemicals, so they are just sent back here in order to avoid the loss of water with the feed again pass through the membrane and get separated, while these organic chemical which has been separated and they just get lost as from here. By the way, I think here it should be organic chemical layer should be above than this water layer, because this is usually lighter as compared to the water. So water is the heavier and this is mainly at the bottom. So it's better to present it like from here water, and from this layer these are organic chemical. As in industries we have like such kind of three-phase separator in which top layer is just vapors of hydrocarbon, then next layer is hydrocarbon liquids, and then the last layer is aqueous layer. So here permeate after condensation, permeate which pass through this membrane after condensation, water rich phase that is recycled to the membrane system, that is used water rich phase which contain large amount of water and some small amount of these organics, that's water rich layer, and nearly pure volatile organic chemical phase is separated from here. One thing here I want to mention, like he has mentioned hollow fiber module. For some application these can be used where you can apply them, but most of the time in these pervaporation on the large scale, when you have to use, most of the time plate and frame are used, but hollow fiber are also used for some application. Like in this application he has mentioned there, volatile organic chemical removal from water is taking place with the help of hollow fiber module. And retentate is pure water. Retentate the pure water which we were looking for, which we were expecting to be pure, so that's pure, that contain less than 5 parts per billion of these volatile organic chemical. Very small amount they will be available, and that's fine for us. So that's it. In this lecture we started with the pervaporation. What is pervaporation? Its introduction, like pervaporation is a combination of two words, perm selective, and then there is evaporation. And through this membrane we have seen that when separation takes place, so after passage of permeation of the liquid species, they get converted to the vapor on the other side due to application of vacuum or due to very low pressure as compared to their as compared to just some ambient pressure. So their application is mainly for removal of water from hydrocarbon, like from ethanol, ester, ketones and other hydrocarbon, as well as for separation of closely boiling hydrocarbons. They are used for this. These pervaporation membranes are used, and the mechanism here is when these liquid pass through the membrane, on the other side you have a vacuum and they will get converted. Here most of the time you use asymmetric membranes. These are used because the phenomena which you are looking for, you are applying the vacuum, and if you apply porous membrane, then vacuum will be transferred to the other side and you can't maintain. On the feed side there should be high pressure, and the other side, permeate side, there will be low pressure, this vacuum. Due to this you apply the dense membrane, and mostly they are layered, sometimes 3 layered membrane structures. One is dense top layer, active layer, then there are 2 porous layers. And finally material should be selected wisely based on either you want to separate the water through those system or you want to separate hydrocarbon, and we will prefer it based on the application. Like if water is in small amount, then water should be allowed to pass through the membrane, and if hydrocarbon are in small amount, then they should be allowed to pass through the membrane. And when you allow the water to pass through the membrane should be hydrophilic. And then you are separating the hydrocarbon through the membrane, permeating hydrocarbons organics through the membrane, then it should be hydrophobic. It should not attract water in large amount. That's it. Thank you. With this we have concluded this membrane topic. So next topic which we have to discuss is leaching. We have to discuss that briefly in next lecture. So thank you.